Okay, so the last topic in circular motion and gravitation. So now we're going to talk about energy. So we know that, say, NASA wants to send a spaceship into space. What they're really interested in is how much energy, like fuel, because fuel gives energy, how much energy is required to get that spaceship into orbit around, say, the Earth. Or you might want to need to, how do you get that shuttle to Mars and drop a probe onto the surface of Mars? So they need to know very precise energy calculations. So in grade 11, we learned the following equation. Work is equal to force multiplied by distance. So we know that we need to exert a force to get an object into space. But then we're also interested in how far it's going. But what makes this equation or this scenario a little bit challenging is that as we get further and further and further from a massive body, we know that the force of gravity, that force of attraction, is getting smaller and smaller and smaller. So if we actually were to graph, so our force of gravity equation is equal to gmm over r squared. So we can see as F is proportional to 1 over r squared. So we're assuming that the masses, again, it gets even more complicated because as a space shuttle is leaving Earth, it's expending fuel. So it's actually getting lighter and lighter and lighter. But we're going to go with we're going to focus on that R value. So we're going to say that assuming the masses of the two things remain constant and R is getting further away, R is getting smaller and smaller and smaller, we see F is proportional to 1 over r squared. So if we do a little graph of showing the relationship between F and distance, we get the following. So for example, this dotted line right here, this will represent the radius of the Earth. But as we get further and further and further away, we see that the force required to get away gets smaller and smaller and smaller. And we know that since work is equal to force multiplied by distance. So work is this energy, that change in energy. So how much energy is required. And force and distance. So what we can see is if we multiply force by r, so the y-axis by the y-axis, that will give us our energy. So we need to find out what is the area under the curve. So the area under the curve, that will give us the energy. We look at that, and that's actually a very complicated area. We can't just say, oh, what's length times width? It's this smooth, continuous curve. So we'll actually give you the equation for energy, but for those that have already done a little bit of calculus, we can actually integrate our expression for energy. So you can see right here. So F is equal to gmm over r squared. If we integrate, if we just focus on that 1 over r thing, because again, the gmm is just a constant, so we can just pull that gmm outside, like so. We have gmm outside as a constant, doesn't affect anything, 1 over r squared dr. So if we integrate that, we get the expression negative 1 over r. So all that's happening is that if we want to calculate potential energy, we get potential energy is equal to negative gmm over r. Now the question is, why is it negative? And negative is just convention. So remember from potential energy, if we have, say, an object, and we drop that object from one height to another, we can see that the potential energy here is some quantity, and potential energy here is some other quantity. But in itself, it doesn't really mean much. What is important is being able to compare the energy at two different locations. So I could have said, maybe the potential energy up here is 10,000. Or so let's just say 1,000 joules. The potential energy down here is 0 joules. The difference is 1,000 joules. But at the same time, I could have said, oh, up here is at a potential energy of 750 joules. But if that was the case, down here would be negative 250 joules. The difference is still 1,000. So it doesn't really matter that if it's a negative value or positive values. What's important is the potential energy at a single point is just a number. But when we compare it to a different location, they'll give us what we're actually interested in. It's that change in energy, how much energy is required to go from point A to point B. So why is it negative? Let's just scroll down a bit. So here's another picture. The reason it is negative because when we're way, way, way out here, so when we are infinitely far away, so here's our equation. Energy is equal to negative GMM over R. When R is really, 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 really big, so we divide by a really, really, really big number, we get a value of 0 joules. So really far out is 0 joules. However, if we want to move away from a massive object, we have to do positive work. So the only way we can get to 0 by doing positive work is we have to have negative potential energy when we're closer. So for example, if our energy, if we're starting right over here, our potential energy might be equal to 5,000 joules, negative 5,000 joules. If I want to move away from Earth, I have to do positive work. So I have to add 5,000 joules of energy to my system in order to get to this infinitely far away position.